Let's start. We're going to talk about, again, I guess I'll be redundant, distributed stream processing over thousands of data centers and some of the challenges that we face at Akamai while doing stream processing at a large scale. A little bit about me. My name is Alex. I just joined Akamai about 5 months ago. I'm an engineer there. In a previous life, I was the CTO of a company called Concord. We were a distributed stream processing engine. I'll talk about it in a second. Right now, we're currently building an IoT platform for a third of the internet. So hopefully some of these challenges, if anything, it'll be fun to hear about. You can reach me at on my Twitter. That's obviously, opinions are my own. Sometimes I may be offensive, but otherwise, feel free to reach me at my Akamai email. So that's it. So a little background about Akamai, just so that everyone is on the same page before we start the talk. Akamai is what the telco providers call the middle mile. And so this is a graph from AT&T about sort of the world's internet. And as you can see, it sort of like works around this large metro areas. There's like a high condensation of servers here. But then if you are a user and you're trying to get to the other side of the world, you typically will get routed through Akamai. If you visited any website, it's likely that you download content from Akamai through the CDN and HTTP traffic. So what Akamai is actually Akamai has a ton of these little data centers and these little connections, and this is where I want to highlight a major difference that shapes the software that we write at Akamai, is that when you think about a difference between a cloud provider, let's say Google or Amazon, IBM, Azure, whatever it is that you're using, and the difference between that and someone like Akamai is that we actually don't have massive data centers of 50,000 computers. We have tens and tens of thousands of data centers that are very close to the user. So our network by section is huge, but it's because it's distributed throughout the world. So this should be the picture that you guys keep in mind as we go through the rest of the content. This is the architecture that we have to work with. This is the major constraint, is that we operate on a WAN-first environment. And so when you launch up your EC2 instance, you sort of get this implicit guarantee that you'll talk to a computer that's either within a rack local or within a couple of miles, and you have some bandwidth and latency guarantees. That's not the case for us most of the time. So I wanted to highlight this picture. This is available for anyone to see. It's called the Akamai Globe. And on an average day, this is just a picture I took a few days before this presentation. We're doing 36 million requests per second just on one application, exclusively on HTTP traffic. This doesn't include any HTTPS traffic, any VPN, any sort of the other hundreds of products that we support. And so this is the scale that we have to work with. And I'll point out a few things about this. The dots are the data centers that we have around the world that support HTTP traffic. And so when you're trying to stream data, let's say from a northern tip of Colombia to Florida, right? You kind of go through all of these little dots, and until you get there. And because we have a huge control of the internet. I think we pass about 1/3 of all of the internet traffic goes through Akamai. We have an excellent routes and network latency at a global scale. In particular, this picture, the height of the bar is the number of requests being served by that data center. And if it's orange, it's kind of, that sort of indicates a little bit of capacity. And so those are just highlighting the same architectural constraint that we have to deal with, which is the notion that we have to operate on a WAN-first environment. To take an example, I went onto that globe and I clicked any random point, and I landed at Yellowknife, Canada, and I've never heard of that city in my life. And so, but we do that whether it's in Canada, in a very cold place, or it's in New York, right? The business model that Akamai operates in is this smaller data centers very, very, very close to the users. So in New York, we might have 100 data centers or something like that, and they vary between 3 computers as here in Stony Brook and Yellowknife, Canada, or a couple of thousand computers. And that's our deployment model. And so it works very nice for content delivery. And I'll talk about the difference of bandwidth as we try to build the distributed stream processing, which will invert the edges of the computational diagram that you have in mind. Just for fun, I Googled. I've never heard of this city in my life. And so the temperatures go up to -53 Celsius to 37 degrees Celsius. So we don't have a whole lot of users there, and so we only have 3 servers there. Usually for smaller data center deployments, we'll partner up with ISPs, so we're actually co-located in the same physical space as the internet service providers, which gives us this excellent traffic and latency guarantees to our upward links. So I joined Akamai as part of the Concord acquisition in September of last year, and for the first few months, I've spent my entire day full-time designing the system that I want to talk about. So that's my background. A little bit about Concord. We come from an ad tech background, and the most important thing was to always serve ads, and serve ads under a strict latency guarantee. So we would serve ads 100% of the time under 30 milliseconds, and the whole ad optimization pipeline was optimized in under 50 milliseconds. That means that between the time hundreds of thousands of users were clicking an ad until the time the bid and the optimization and machine learning pipelines produced back to the edge on the ad server, that took exactly under 50 milliseconds. And so that was the inspiration for some of the architectural choices that we made at Concord that Akamai thought compelling, and so we joined them and my whole team. So a little bit about Concord. It is a C++ built stream processing engine. It is built on top of Apache Mesos, and so it was designed for relatively low latency. It was inspired by Google Millwheel and a lot of the Tyler Akidau's work. And now I think if you've heard of Google Dataflow, right? So the Apache Beam style API that runs on something like a Concord framework. And so we more or less we were inspired by that paper, but we had all of the constraints of not running in a Google environment, and so a lot of the architectural differences come from that. At its heart, Concord is a global pub/sub mechanism. And so if you've used Kafka in the past or RabbitMQ, or you've had your own queuing system, you publish to names, right? They're usually stringly typed streams, like you're going to consume from words, and operator A in this instance is going to produce on a stream called words. And so that's how you compose jobs. It's sort of very dynamic, and it's designed to be modified at runtime. That's one of the main characteristics that drove the computational model. So let's say that you were running and you had 2 classes of code, like an A microservice and a B microservice, and now you have a C microservice, but it wants to subscribe on a different grouping mechanism. So here, this group by is similar to the SQL group by when you say select star from this table and give me the grouping. Shuffle is a different grouping. If you've done streaming, there are typically 4 or 5 different grouping mechanics that are useful to do stream processing. There's the group by for consistency, and so you could do customer aggregations, that kind of stuff. Shuffle is for load balancing, and there are other strategies like round robin and random, etc. So the idea behind Concord was there's a simple API, and so it usually had 3 methods: process record, produce record, and process timer. And so when you distill down at its core, what are the primitives that you need to do stream process? You need some sense of time. You need to be able to punctuate continuous data streams and produce it to a database, or produce it to a dashboard, produce it to someone So that's the timer API, and then you somehow have to process records, so effectively a byte array. And the language, when we were working at an ad tech, we were writing all of the parsers in or the front end in low-level languages, and all of the machine learning techniques we were writing them in Python. And what we wanted to do was a consistent API across all of these languages and a consistent runtime with consistent performance guarantees. What Mesos gave us was multi-tenancy, effectively, right? And so we were one of the first, if not the first, enterprise framework written on top of Apache Mesos. So it is, if you guys have heard of Kubernetes, I think there was a talk earlier. Kubernetes was also influenced by Mesos, and some of the shared work that they did with Google. And so what Mesos gives you is that it represents an entire cluster of computers as usually 3 numbers that you're interested in: CPU, memory, and disk. And now they added GPUs. Well, you can add arbitrary tags, but so it gives you, it abstracts the hardware onto these malleable components like CPU, memory, and disk. And then what you do with that is that you write a scheduler, and you tell those hardware components where to run code. And so that's called a two-phase scheduling mechanism. We use Apache Mesos for that. But what it also gave us is that it was embedded with the containers, right? And so it was natively, when we first started working on this, it only supported, I think Docker support had just landed upstream, and so it only supported basic C groups and namespaces and basic seccomp profiles. So it gave us task isolation. That means that you could run multiple workloads in the same physical cluster without fearing that your QA or your test engineer was going to take down your site. And so for the machine learning pipelines that we were developing, we're like, okay, fine, deploy as many as you want as long as it has some constraint guarantees. We don't care. It'll crash, it'll die, but the rest of the cluster will have the SLA guarantees that we cared about. And that gives you, so in addition to that, we wanted the cluster to be highly available. So if the scheduler died and people were submitting work, so we wrote a state snapshotting algorithm that works with Zookeeper and Mesos to figure out the state in case of failure. And so like I had said, this container environment gave us multi-tenancy, and it also, but most importantly, the main thing was it gave us hot code deployment and dynamic topology changes. And so if you have a pipeline and at runtime you want to change the number of instances that are your ingesters and so on, you can simply scale up that type of workload. So what changes is your concurrency and your parallelism semantics are divorced from your software engineering practices. That is, if you have high load, you don't have to go back and change your code and say, oh, increase the number of threads to 10. You just tell your DevOps to increase the number of running containers in your cluster. We built in a tracing engine so that we have an idea of the performance characteristics. We had an embedded router so that we can send other containers traffic. What was compelling, very compelling for Akamai is that although you could compose these things dynamically, you can compose each step in a different programming language. That means you can have upstream dependencies in Python and upstream dependencies in Ruby and upstream dependencies in C++. It didn't matter. We abstracted the communication layer into a C++ proxy that is similar to what Nginx, if people are using, or HA proxy. And so the code, the user code, will talk to an embedded sidecar process. And that will control all of your sockets. It will control the memory usage. It will do retries and sort of all of the intelligence that you need to build resilient applications over a network. And so the key here was that a lot of our clients before the ad tech, but particular a lot of Akamai clients, internal clients too, want to be able to change the running characteristics of a computational diagram without taking the cluster down. And so if anyone here has experience writing Storm and where you package this very fat jar, this Uber jar, and like you tell Nimbus to distribute it to a bunch of worker nodes, and then they start doing stream processing and you made a mistake, and now you have a bug in the middle of a computational pipeline, okay? And in order for you to fix that, you have to tear down what's running in your cluster and fix the bug and try it again, and that's basically downtime. So the main thing here is that we wanted to be able to subscribe and publish dynamically. And for people that have used Kafka, it sort of sounds absurd that you have to take down an entire DAG of nodes running just to be able to fix a bug in a small part. But that's just how it's done today. In addition to that, we wanted to scale the number of instances at runtime, which we talked about a little bit. And so at a high level, right, it's a directed acyclic graph of computations, where each node in the DAG has a dynamic number of instances that is malleable by a DevOps or a SysOps or whoever is managing your network. We first wrote our own distributed tracing infrastructure, and so this was also based on a different Google paper, which was based on Dapper and Xtrace from a couple of universities and so on. What it is that at the source of your computational graph, you taint a packet. And so let's say you give it a color like purple or red, it doesn't matter. And anything that touches that packet will also emit metrics. And so you get this distributed trace and this dependency pipeline that says that this path took 150 milliseconds, but this other path took 50 milliseconds. And so one instance of it is not particularly helpful because it just says, well, this took, it's kind of when you open your Chrome windows and it says that this resource took 150 milliseconds. What's useful is the trends that gives you, right? So if you're pushing this to a data store, then you know that subsequent deployments of this one instance of a fraction of a computational pipeline had increased the latency and failed your SLAs. And so you know when to debug, how to debug, and so it makes debugging relatively straightforward, really, when you're having both latency or throughput issues. Concord is fast. Currently, we do about 1.2 million messages per box on some, Amazon boxes. That's where we did this test. And we have relatively low P99 latencies. We're doing 8 milliseconds. End-to-end on that. We also have, so it's 20 milliseconds for larger payloads, but what we're pretty excited about is we have a prototype, and Akamai has multiple user-level TCP IP stacks that they've built over the years. We brought our own too, and that gives us 17 microseconds to send a request to a computer and get back a response with fully serialized types. Because we wrote this proxy engine, this Nginx lookalike, we can swap the delivery guarantees of your pipeline without you changing a single line of code. And so as a user, it's really helpful in saying, oh, I want to process the logs exactly once, and I want to process the logs at least once with Kafka, right? And so we first wrote this for a super low latency scenario, which was basically ad tech and finance, who were our first clients. And we didn't want to pay the cost of replication, okay? Because the temporal value of the data was so high that to replicate the data would lose half the value. You can typically replicate data to 3 times and then send it upstream within that few milliseconds, let's say 10 milliseconds. But we had a lot of clients that were doing Kafka-style stream processing. So they had these billing logs or these pipelines from jobs, et cetera, and they wanted to do these transformations on them. And they understood the at least once delivery of that system. And so they just wrote these Concord operators, and it was abstracted away from you, right? So as far as you're concerned, again, you only have those 3 or 4 methods, which is a class in most programming languages. And now you get to choose the delivery guarantees. In addition to that, each language gets to choose that as well. So a little bit about stream processing. This is about 2 slides on that. Stream processing is the idea that you never stop processing events. And things that you usually do with events is that they usually have a timestamp. And so a common example are telemetry or logs. These events are immutable, right? They're facts. They happened sometime in the past, and that's it. Like, you can't change the fact that it happened. Currently, most people do very simple transformations and filter and aggregations, but when they unlock the potential of a distributed stream processing engine, they start doing much more complex things. Like, they start sampling from a larger arrays of processors and doing much more interesting machine learning techniques that minimize some cost function like network traffic. In particular, streaming is a superset of batch and is designed with principles of unordered, unbounded, and varying time skew events in 2 time domains, event time and system time. And so they are unordered. Actually, I'll tell you guys a funny story. My first week here, we went for beers in Cambridge, next to the MIT campus where Akamai is headquartered. And we were having beers, and one of the service perf guy goes like, "Oh yeah, we had an incident today." And so I asked, "Oh, well, what's the incident?" And he goes like, "We had a data center that came back after 2 years of being dead that we weren't able to access because it was in a hostile country." And so you can't guarantee the ordering of these events, right? Like, somebody's going to turn off your data center because you have computers in very hostile countries, and they'll just unplug the power. And I think that the data center was maybe from Turkey, I'm not sure. And so you have this massive data center failures. You have to reconcile those failures and what that meant. For that particular job, the incident wasn't the fact that the data center came back online and was serving traffic correctly after a machine rewipe, which is automatic. It is the fact that it kicked off this exabyte data processing pipeline that was trying to rebuild users for 2 years of data. Let's see. So varying time skew is, so traffic spikes is the norm. We may get 10x on that HTTP traffic at, of 36 million requests per second. That's just for one application. Okay? And we have hundreds of applications that have similar traffic characteristics. Because of the nature of Akamai being a CDN as its, one of its major businesses. Let's see. So what we have now is we have 99 problems, but distributed SQL isn't one. When I was drafting this presentation, our equivalent of our Jeff Dean basically posted on Twitter that we had a distributed geo-replicated in-memory SQL working in 1999. So the scale that we're dealing with is that right now, I think across the company as of a couple of years ago, we do about over 1 billion MapReduce jobs for the entire company. And just for the streaming data, we're doing about 7 petabytes of streaming data per day. So a missed opportunity is missed money effectively. And so let's say that somebody gives you an error budget and they're very friendly and they'll, oh, you can fail 1 tuple out of every million tuples that this stream processing system sees. And so at the end of the month, you could have lost effectively $93 million. The reason this is hard is this is how you think about the system, right? So you think about the system in the general Amazon data center stuff, right? So before we joined Akamai, we used to serve clients that worked on Google and Amazon and Azure, and they have this super nice computational models. The first one is that they'll give you a data center and you go on the UI, and then with each data center, you have regions and you have connectivity guarantees. This is how you generally design software. But the truth is that this is actually how Akamai works, right? And so the bandwidth increases, the bisectional bandwidth on this side is huge. And so if you're streaming the Olympics, there's a tremendously complex caching hierarchy to get the Olympics from this side over onto wherever the local data center Olympics are happening, back to the router backbones, to people in New York or here in Krakow that might be watching this, or if we were to live stream this, this event would be the source of the data. This is actually how it works, and this would be the edge. Oh, next slide. This is the one thing I wanted to highlight here. Again, what we're trying to do is distributed stream processing over thousands of data centers. And So the idea here when we started working on this project was that we are great at distributing content, okay? And we have all of this machinery and physical compute. We have hundreds of thousands of computers around the world in probably almost every major city in the world. And we have this dedicated bandwidth and all of the infrastructure that is required to deliver software there secure, reliably. And so what if we inverted the edges? What if instead of pushing out content, we were able to consume content? And that's when the Concord deployment paradigm kicked in. And so you may have lights or cameras or cars, and they just want to send data, and you have to do something useful or interesting with them. In fact, Akamai is a multi-tenant company, right? So we host probably the largest enterprises in the world, and they want to run their code on the edge. And nobody can deliver that because no one has the data centers, the physical computers deployed at the edge to be able to do this, but Akamai. The problem, though, is that this is actually a data distributed engineering pipeline. That's the department I work for. This is actually, that's a snapshot of a pipeline. I just sort of blacked out the labels of it. But this is what we have to do at the edge. So you have this relatively, tiny data centers, and you want to do that. And you want to do that under millisecond latencies. And then you want to push up those streams so that people can consume those streams intelligently. An issue to highlight here is that you lose bandwidth as you get closer to the user, right? So the user may have, let's say, a gigabit uplink and downlink, and then at the first tier of cache, we have probably terabits of data, and then here we have probably hundreds of petabytes of data that are closer to the user. And so the bandwidth expands, obviously, because we have thousands of data centers at the edge right next to the users, but when you invert the edges, you have to do it intelligently. You can't just shuffle that traffic to the pipelines, or else it'll break, and probably break a third of the internet if that was to happen. So this asymmetric network, right, makes it weird in that you usually have trade-offs, right? And the general trade-off is that you trade latency for bandwidth and for throughput, which usually uses more bandwidth. But here, this asymmetric network layout, as you go up through the root of the nodes, all the way up to the user who's seeing like a dashboard of some form, or maybe this could be a different car or a different light or whatever, the bandwidth between the edge and that device, the characteristics of that traffic is very differently. And so the changes that we made were particularly focused on scheduling and security. And I want to give some highlight as to how do you do stream processing securely in a scalable fashion. So these are the main things that we did. Sharma Padilla, who's a guy that wrote Netflix scheduler called Fenzo, did this great presentation, I think this year at GeeCON or a couple of years ago. And so I basically stole his idea of how to present it, and this is the distilled form of that. Is if you're trying to place work on a cluster, right? So you have a set of machines. You could either do this first fit scheduling, which is, there's one computer that has 2 gigabits of RAM and it has 10 cores. It's fine, it fits, just put it in there. Okay. The problem then is if you schedule the first 10 tasks on the first 10 machines that have GPU support, and then you deploy a machine learning pipeline, you have outstanding work, idle resources, and you can't move forward. You can't make progress because you've scheduled it poorly. And so there is a trade-off between the latency of the time that it takes for you to make a decision of where to place work, and the accuracy. And so what you want to do is, I'll highlight a thing here, is you want to pack as many things together on each server as you can. The reason is, if we're not using that capacity, we're still paying for power, for bandwidth, for all sorts of things. So when we have idle machines, we now have the capacity of just eliminating that machine. We'll turn off the power, who cares? Okay. So in particular, we had a major redesign for multi-tenant clusters, and I want to talk about a couple of things which I don't think are being done in a lot of places right now. Mostly we added an autoscaler component, which it gives you a task, and it somehow monitors some SLA guarantees. So you might have an SLA that says, oh, I need to respond to clients in 30 milliseconds. Or, oh, I need to push this pipeline, this gigabits of logs upstream, so I don't care about latency, I care about throughput. So you write this arbitrary logic constraints, and you say, autoscaler, as long as I'm meeting my constraints, autoscale me up until the time that I'm not. And so when you are meeting and you're exceeding your pipelines, you have lower latency, or you're shuffling too much data through the network, we'll just simply deschedule you. And so it kind of runs at a near optimal level of utilization in the cluster. And I want to talk about some very difficult things, which are the legal requirements of what that means. So at its core, we have this monitoring set of processes here. So every multi-tenant client gets a set of supervising processes. And this is all running on a set of random machines around the world in these edge locations. And we have to monitor their nodes, not only so that they understand what's happening with their code, but because we want them to still have SLAs. So our clients give their clients, usually users, like SLA guarantees, like their website is slow or so on, or they want to do spam traffic or bot detection, or they're doing some security manipulation. So we need to make sure that their jobs are up and running. But we also want to make sure that the code that could potentially run inside Akamai is also meeting some SLAs that are application driven. At its core, I built a multi-level queue for the system. And so it's pretty much what you would expect out of a FreeBSD-like scheduler, where there are these non-preemptible resources like your DNS, your mapping processes in a cluster, your name resolvers and so on, your certificate manipulation, your key management infrastructure. Then you have the user code. Something that we added that isn't sort of surfaced in a lot of places is this notion of a test group. And what it is that it's bounded. In each geographic region, we want to be able to deploy this hostile traffic. And what I mean by that is that it might consume a lot of network resources, it might consume a lot of CPU, it might be oversubscribed, but we don't care. And so we might schedule these containers, and you can think of them as Docker containers, at the edge on an oversubscription policy. And so we can just kill them at will, and they're usually for engineering and debugging. So we have a lot of very difficult things with constraints with legal. That is, the data that is in the EU can't leave the EU. That means the DNS queries, the IP information, data has to be encrypted on disk and on the wire. And so that we have to then add those because we operate at a global scale, we have to add those constraints into the application scheduler to make sure that we don't violate that. Otherwise, we'll get sued and bad things happen. And so we want to still do this low latency, but we have a ton of optimization goals to achieve. So we came up with the idea of an island that is bounded by the latency of the decision making. So if you can say, oh, I can afford a 1-second task placement on a cluster, or 5-second, or however long it takes on, I'll say, an AWS, like 30 seconds to spin up a machine. Then that's it. That's your minimal latency, which means from the time that we receive the request, the maximum edge that we can cover would be the latency to achieve consensus to place that task in any of our data centers. Something that we've added, which I thought was the coolest thing, was our security infrastructure is extremely mature. And this is something I've never done before. And so I was a startup kid, and we were just effectively just writing features and writing code, and we thought we had a great product. And then we came here, and they're like, oh, your thing is broken. It's terribly insecure, and it's not designed to run in the internet environment. And so what we do to keep customers safe is that each of these dots are containers, okay, so tasks. Each one, and this runs in one particular data center. So one of those dots that you guys saw in the beginning, that's one of these things. And we have to make sure that the lifetime of the communication certificate between any of these 2 points is authenticated and encrypted, which means that the certificate, the SSL certificate that gets issued for this container on this data center on this particular rack is ephemeral. So when that container dies, we expire all of the accesses that that container had access to, what it means to be that task, what it means to participate as that customer's security infrastructure and so on, and we revoke it when it dies because we know deterministically when the container dies. On the root trust of that, we have this master key which effectively gets rotated all the time. So some future work is we want to work on hierarchical scheduling, and so at this moment, because of the legal constraints, is something that my team hasn't solved yet. We have plans for it, but I'm not sure exactly how to, optimally use these clusters here and fail over to large geographic regions. So we have so many computers that we can host every single customer in one data center. So right now it's not that big of a constraint, but we are onboarding more and more customers. So I want to make sure that there is a tiering level. And so that tier is now manual. And so when you sign up for Akamai, you kind of sign up in the same way that you sign up for Google, and you say, I want EC2 East Coast or EC2 West Coast, region A, B, and C, and then we map that to a logical overlay of the world. And so let's say for Europe, we might have data centers here and in Paris or wherever it is. And so I want to work on an algorithmic version of that. I want to add the streaming DSL of Apache Beam. I think it's the best DSL for streaming that exists today. And some of the exactly one's runtime. So we have this great now user level TCP IP stack, and we get 17 microseconds between two computers. So what can we do to improve the experience of developing software at the scale that we develop software? So I want to surface that as an exactly one's runtime, which means that you're paying the replication of data tuples for every single data tuple, for every batch of tuples. Because we're so fast, we have so much network, we can get away with that at a regional level. There's no way we can get that at a global level, but that's fine for most use cases. So finishing up a little earlier today, but we do all that so that you can do real-time analytics on the lights of your house. And with that, I'll leave it so that people can ask questions about any particular technology. All right, I'll stay here and I'll answer a question in case anyone wants to come and talk to me. That's it.